Okay, the first actual lecture segment that we need is from chapter 1, which makes a lot of sense. We're going to start in chapter 1, and actually this week we're going to encounter content from chapters 1, 2, and 3. So I apologized for front-loading the summer a little bit with lecture videos, but they're going to be relatively short given how much work we're going to be doing to get into the consequences, the physics of what's going on, and work through it in class. There's actually surprisingly little that needs to be presented this way. Chapter 1. There's two things I want to talk about in chapter 1. And one of them is units, and the other of which is error tracking. So I'll divide the lecture into two segments, one for units, one for error tracking. This is the one about units. If we're going to be scientific, if we're going to be quantitative about the observations we make, about the way things move and the way the things we see happen, if we're going to be quantitative about that, then we need to be able to refer to a reliable system of measurement. If I say that this desk over here is 7 dogs long, that means a lot to me, I suppose. But which dog am I talking about? How do we standardize that? What does that mean? So we'd like to agree on a fundamental system by which we can describe quantitatively the measurements we make. There are 3 fundamental ways that we humans can measure the world around us. If a lot of what we observe is motion, the movement of a thing from that place to this place. Quantifying that means a way to quantify a place. And we'll talk a little bit about this in one of the next videos coming up. But if we're going to measure a place, that means we are talking about how different is this place than this one? What is the amount of space between these 2 points? What is the spatial extent of the thing? How much space does this measurement take up? Whether it's the length of a table or the distance between 2 points, how much space is described by this thing that I'm being quantitative about, this measurement that I'm making? I'm going to call that the dimension of length. I'll use a capital L for dimension of length, and I'm going to put these symbols in square brackets. Anytime I want to talk about a dimensionality of a thing, in other words, in what kind of fundamental measurement is it? Is it a spatial measurement? Then I'll say it has the dimension of length. And the unit that we'd like to use to express these measurements of spatial extent, there are, I'm sure you can list about a dozen different ways to measure length. We'll use the metric system, and we'll use base metric meters. Lowercase m is our symbol for that, meters. The meter is the basic unit for spatial extent. Cool. If we're going to talk about something moving from point A to point B, we might be interested in comparing the motion of one thing from point A to point B to the motion of a different thing going from point A to point B that was faster. Something about the motion from between the 2 points was different, and what really, when we say faster, what we mean is that it took less time. What is the temporal extent of the event in question? How much time is described by the measurement that we're making? How much time is there in this interval? Temporal extent. Another dimension, capital T for time. And the units will use seconds. The third way that we can be quantitative about what we're observing if we talk about this position here, as of right now, there's nothing there. Well, I guess there's some things there, or air, I suppose, or the area rug on the floor that you can't see. But now there is stuff there. It doesn't matter really what it is. It's a person, it's a dog, it's a tree, whatever. There is some more matter there than there was a minute ago. And that's the other fundamental way that we can talk about the world around us, and that's to describe the material extent. How much matter is described by this thing that I'm measuring? How much mass? Dimension of length, dimension of time. Square brackets indicates a dimension, one of these three fundamental ways that we can talk about the world. It's the dimension of mass, m for mass, and this gives me a good chance to point out the typography that I'll use at the whiteboard for the rest of the summer. If I mean a capital letter, I'll add little feet on the bottom so that we know that this is a capital M and that's a lowercase m. So that's a capital. Anytime there is ambiguity in whether it's upper or lowercase, I'll make sure that it has the little feet on the bottoms or tops of the letter. So for example, there is a lowercase s on the board right now. If I, for some reason, wanted to write a capital S, I'd make sure it had the little feet, or hands, I suppose, whatever they are. Serif, I think they're called. The unit we'll use for mass is the gram. But the French scientists that originally introduced the gram standardized it wrong for us. The size of unit that is most convenient for macroscopic objects moving around, the kind of measurements that we make in real life, is actually 1,000 times bigger than this. So let's agree to use the kilogram, and as you know already, kilo is a prefix that indicates times 1,000. So we're working with the MKS flavor of the metric system, which might be different from the system that you used in chemistry, the CGS, centimeters, grams, seconds. And that's because generally we're dealing with larger things than that. Okay. So yeah, we come up with a measurement, and we can talk about its dimensionality. So, for example, suppose we wanted to measure the density of a thing. We would ask for its mass and divide by its volume. And we find the volume of a thing with length times width times height. So this has the dimension mass. Volume isn't its own fundamental way to interact with the world. It's the product of a length, and a length. So we can say that it has the dimension of length cubed. And every volume, whether it's liters or cubic feet or gallons or meters cubed, has the dimension, the fundamental observe the world dimensionality of length cubed. So if sometime later we're doing a problem and we end up with some sort of expression that turns out to have the dimension of mass per length cubed, we just found the density of something. Or at least it's something that looks like a density. This is one way that the dimensional analysis can help us. And there's another way. Suppose we're solving a problem and flipping through our notes and we find an equation written down that I'm going to use an example that we know is incorrect. Talking about density, mass, and volume, and we find this equation written down, and we go to use it, and the online homework system, Mastering Physics, I'll say more about that on Monday, says that we're wrong. Well, what happened? And you know this already. This is the wrong equation. It should be density volume equals mass. But if it's a less familiar equation, one that maybe I just introduced in lecture and we copied into our notes backwards, you know, that happens. It happens to me all the time. Dimensional analysis is one way that we can figure out, that we can identify the fact that this equation is not correct as it stands. Density, the last time we talked about density, has the dimensions of mass per length cubed. Mass has the dimension of mass, and volume has the dimension of length cubed. And there's no way that this left-hand side can equal that right-hand side. This is not an equal, this is not a good equation because these two sides are not equated, they're not equal. So dimensional analysis is one way to help identify an incorrect equation, something that we copied down wrong from somewhere. Okay, last thing about units, and that's to mention unit conversions. We won't spend a whole lot of time working on this explicitly, but it is a thing that we're going to have to do. And so I'll just point out the way that I prefer to write things, and anytime we're working through a unit conversion together, this is how I'm likely going to write it. So just introducing how that's going to look. Suppose, okay, so I get in my car and I drive to the grocery store, and along the way my speedometer says 30 miles an hour. Miles per hour is not base metric. In order to express that measurement in base metric, we would need to figure out how to convert from miles, which is a unit of length, to meters, and from hours, which is a unit of time, to seconds. When we say per, miles per hour, that's a fraction line. Anytime we say per, that's the fraction line. Miles per hour. So let's pretend that miles and hours are variables, and that when we multiply by a fraction, if we had hours in the numerator of that fraction, then those hours would cancel, like they were, you know, x and x on both sides of a fraction line. 1 hour is 60 minutes, and 1 minute is 60 seconds. And we can see the strategy here already, that hours will cancel hours, minutes will cancel minutes, and we'll be left with seconds in the denominator, which is where we want it, meters per second. Miles is a little bit tricky. We can look up actually, as long as we're looking stuff up, we can look up directly the conversion from miles per hour to meters per second. I never remember that one, and that's okay. I remember all these other ones, and that's fine. So likely when you unit conversions, it'll be nicer than this because you won't need to remember 17 conversions. All right, so miles to feet. I remember that one. 1 mile is 5,280 feet. Miles is in the numerator, so in order to cancel it and not talk about miles anymore, we need it in the denominator. 1 mile is 5,280 feet. 1 foot, again in the denominator, is 12 inches. 1 inch is 2.54 centimeters. Why do I remember that? I'm not sure. Is it something that you need to remember? No. Anytime you'll need unit conversions, they'll be provided to you. Again, this is just to illustrate the method. The X on the next line like this means keep multiplying. Centimeters to meters, hold on, centi is 100, like cents in a dollar. So $1 is 100 cents. So 1 meter is 100 centimeters. Now that we've stacked a fraction multiplication like this, we can multiply all the way across all the numerators, get a numerator, multiply across all the denominators, get a denominator, and then simplify the fraction, write it as a decimal, whatever you want to do. Okay. Fantastic. That's chapter 1. Well, okay. It's the part of chapter 1 that deals with units. There's another part of chapter 1 that we still need to talk about that deals with error analysis. And there's one more part of chapter 1 that we're actually not going to need until Wednesday. But I'm going to post it today so that we have it to refer to if you want to look ahead. Okay, next segment.